Hello, my name is Ijaz and I've recently completed my master's degree in chemical engineering. I work as a consultant for an IT company. Today we will be looking at a software I have written for design of shell and tube heat exchangers. Heat exchanger design is a complicated process. The program can only do the calculations for you, but it cannot decide anything for you. An engineer will still need to have knowledge about the parameters that can be manipulated and their effects. So let's just go ahead and look at the program. When you load the program, you're presented with the screen. Here you can specify the mode, the configuration, the fluid allocation, the flow rates, inlet and outlet temperatures, the inlet pressures, the maximum pressure drop allowed, and the fouling resistance. Let's just go ahead and quickly enter these values. I want to keep things simple for this demo, so we will be working at room temperatures. I will leave inlet pressures blank, same for pressure drops. I will go ahead and specify a fouling resistance, something like this, and 1 or 2. Okay, and let's go to physical properties here. This utility can be used to generate temperature dependent properties. You can specify a stream with up to 3 components, each for the hot and cold side fluid. Let me go ahead and use water here. Same here. I want to keep things simple, so we will just be working with water. But as you can see, you can enter up to 3 components, and there are about 75 of these components in here. I will leave this blank. Let's just go ahead and generate properties. This utility, this part here, would generate the properties at the mean temperature, and this would generate the properties at the inlet and outlet temperature. So we have the temperature dependent properties here. Now there are 2 ways of doing this. You can either enter the values here, the specific heat, thermal conductivity, viscosity, densities here, or you can use the utility just like we did. If you decide to use the utility, the properties generated here would also populate here, so you don't need to enter them again. But you can obviously go ahead and change it. As you can see, this is a required value, so you'll not be able to proceed without this, right? So let's just go ahead and enter this value here. Okay, now on this screen you can define the geometry of the heat exchanger, the head types, A, B, C, D, N, A, B, C, and D, the shell types, all of these are available within the program, and the rear head type. Okay, all of these are available, but we will use the BEM type, the most common one. This is the TEMA class here, the heat exchanger orientation, baffle geometry, tube type. Since we are working with liquids, we will use plain tubes. Here you can set the tube heat transfer coefficient calculation methods. The program defaults to a correlation recommended by HTRI, but you can choose any of these. And some of the most important tube side data can be entered here. I will use 1-inch tubes. You can use one of these standard thicknesses, but I will go ahead and enter a value, let's say 2 mm. Effective length of the tube, as you know, the longer the heat exchanger, the better the efficiency, so we will use this value. And this is the pitch layout. 30 degree leads to the most compact heat exchangers. I will use that. You can enter up to 16 number of tube side passes here, and up to 4 shell side passes. Let me choose okay, we will use stainless steel 304. That is the most common stainless steel grade. Thermal conductivity 16.3. Okay, that's fine. Shell side input can be entered here. Since we are running in design mode, we don't really need to enter all of these values. We can leave them blank. As you can see, we are running design mode, but if you choose to run the rating mode, you will have to enter the value of these 2, but I will go ahead and use design mode. Okay, and if you decide to enter a value here, I will go ahead and use a value for baffle spacing. I will specify a value. The program will honor that, but if you don't, the program will calculate it for you. Here you can enter the fouling information. As you know, fouling is a complex phenomena, and it cannot be defined properly by just specifying fouling resistance, but much work is to be done to come up with models that can predict fouling accurately or the life of a heat exchanger. So we will just use the most simplest type, most simplest method, and specify the fouling resistance. You can also specify a thickness for your scale and its thermal conductivity, and the program will calculate the fouling resistance for you. But I will just, since we have already specified fouling resistance, we will leave these two values blank. Okay, and here you can enter the tube and shell side nozzle velocities, the maximum velocities, but I will leave it blank and let the program do it for us. As you can see, we are ready with all the information, so we can go ahead and run this design. Okay, so now we have a design here. As you can see, heat transfer coefficient 3121. If you consider fouling, it would be 1752. Pressure drop is slightly lower. This is slightly low, but that is fine. This is slightly low. This is roughly 5 atmosphere. This is high. Number of tubes 84. Shell ID is 354. Okay, what we can do is increase the number of passes to 2 and look at the pressure drops. Yeah, this looks good. This is slightly higher. This is higher as well, but that's fine for now. We will assume that this is a good pressure drop. This is acceptable to us. And as you will have noticed, the heat transfer coefficient increased. Same for the fouling heat transfer coefficient, that has increased as well. The tube counts have reduced. Shell ID has reduced slightly, and our design is 2.34%. You have all the information in here. On the summary, you have weight of the heat exchanger and things like that. Now here on all these screens here, you get the output values calculated by the program that are not on the summary of design sheet. So you can find information in here by browsing through this. Tube side pressure drop. The pressure drop is one of the most important parameters that designers try to control. A good design will try to maximize the use of available pressure drop, while this leads to a higher heat transfer coefficient and smaller heat exchangers. So designers will try to maximize the use of the pressure drop that is available to them. Now here you can find information which is not in there, all of the output information. So you can just browse through this and look for the information that you're looking for. Shell geometries, there is some information in here. Heat transfer coefficient values here, shell side baffle cut values here, things like that. Shell side pressure drop is roughly 5 bar or 5 atmosphere, some roughly. Over here you can get an overview of your design of your heat transfer coefficients. There's the clean, dirty, there's the service type, this 2.34 is the over design, so this. And this part here shows you where your resistance is, where the thermal losses are. So as you will see over here, the most losses are due to fouling. This is the fouling resistance that causes over 60% of your thermal resistance. So what an engineer needs to do is work on trying to reduce fouling by using different techniques, by using fouling inhibitors or things like that. But we have identified that fouling causes the most thermal resistance here, so we will need to work on trying to reduce the fouling. Okay, so as I mentioned previously, a good design will try to maximize the use of pressure drop and increase the heat transfer coefficients. Nozzles, here you have information about the nozzles. I don't know why these have not calculated, but I will need to look into that. But this looks fine. Rho v square looks fine. Same here, this is good. This is good. Weight of the heat exchanger, again, since this nozzle weights are not there, it's not come up here either, so that's fine. Weight of the heat exchanger with water in it is 2683. Empty heat exchanger weight is about 1900 kg. Okay, so as I mentioned previously, heat exchanger design is a complicated process. Some of the common design variables include the configuration, baffle geometries, baffle spacing, tube IDs, tube diameters, tube lengths, number of shell and tube side passes. As you have noticed, when we increase the number of passes, the heat transfer coefficient increased. So a designer will need to understand what the effects these can have and what variables can be forced and to what extent. let's see, I can go up to 18 meters, but since let's just assume that I do not have sufficient space, so uh, you're limited to a heat exchanger which is 6.7 meters long. So those are the restrictions that come into picture. So a designer needs to understand that what the restrictions are and what of the parameters can be forced and what the effects would be. So again, if you look at this, the program can also generate a TEMA sheet for you. It has all the information required by TEMA, required by the TEMA specification sheet. So we'll go ahead and close this. We will end this with where we started. I would like to repeat that heat exchanger design is a complicated process, and an engineer needs to know the fundamental principles of heat exchanger design to be able to design effectively. So that's about it for now. I'm in the process of writing a similar program for plate heat exchangers. Please feel free to leave a comment, and thanks for watching my video, and happy designing. Thanks, bye.